Morning calculus students. This is coming to you from Wednesday morning, April 29th. Hope yesterday's little introduction to integrals made a little bit of sense. The fact that an integral is an antiderivative. It's reversing the process of taking the derivative. And when I talked about it a little bit yesterday, I talked about there being two different kinds of integration. There's indefinite integration and there's definite integration. I liken those two different things to derivatives where when we found the derivative, we either found the equation for the derivative or we found the slope of the tangent line. So, but by just taking the derivative, we found an equation that would find us. And then we'd have to put in a value in order to find the slope. Indefinite integration and definite integration work much the same way. Indefinite integration simply finds us the antiderivative. Just finds us the equation that we're then going to use to find the area. And so definite integration, the process of doing that, substitutes some values into our antiderivative and then gives us an answer for an area. So there is a fundamental theorem of calculus that tells us how we're going to find the area. And it's on the board behind me. We'll just walk through it here, and then I've got a bunch of examples for you to do, and that will be it for today's lesson. So the fundamental theorem of calculus states that if f is a continuous function on the interval a to b, so now we're looking at a graph that is continuous, means no breaks between a and b, and I'll draw a little diagram in a second. Then the integral, and this is some notation, again, I'll talk about this notation momentarily. The integral of f of x equals f, capital F of b, minus capital F of a, where capital F is any antiderivative of f. So we have a function f, we're going to take the antiderivative of it, and then f of b, so this function, the antiderivative with b in for x, minus the antiderivative with a in for x, will give us the definite integral, the area under the curve, whatever it might be. So again, what we're looking at, if I draw it over here, is we're going to have whatever function we have, and we're going from a to b, and it's continuous between a and b, and we are finding this area here. All right. Now, this notation here, this symbol, it's an elongated S kind of symbol. It's just simply the integration symbol. It's called an integrand. Okay? And it is just an integral sign. It's just the notation telling you to take the integral, to find the antiderivative. The a and b here are our limits. So the a is our lower limit, while the b is our upper limit. Okay, and so that is what we'll be using when we put in b and a into our theorem here. Okay, the f of x is our function that is to be integrated, and this dx here, this is again just simply notation for the variable of integration. And again, it's like when we had dy over dx, that over dx part was just telling us which variable we were differentiating with respect to. This dx here does the same thing, tells us which variable we are integrating with respect to. All right, so that's a lot of words and a lot of information on one screen here. I think it's going to make more sense as we do an example. Let's go over to the other board and do an example. All right, so over here I've got a little example for us to do. And it's going to be straightforward and fairly simple using our fundamental theorem of calculus. So here we have evaluate the integral. And the way we read this is evaluate the integral from -1 to 2 of x cubed dx. Okay, so x cubed is a continuous function. Here I've drawn x cubed. Starts down here, curls up from quadrant 3 into quadrant 1. And we're going from a, being -1, up to b, which is 2. And we're going to be finding the area under that curve, between the curve and the x-axis. So the first thing we're going to do is we're going to find the antiderivative. Well, to find the antiderivative, we do what we learned yesterday. We reverse the process of integration. So here we have x cubed, so to thinking reversing, we're going to add 1 to the exponent and then divide by that number. So it's going to become x to the 4th over 4. Now when we did integration yesterday, we were always adding a plus c to these. When we're doing it this way now, we don't have to. Because our fundamental theorem of calculus has a subtraction in it, the c will cancel out. It'll become c minus c and it will cancel out. So we don't need a c here. Now typically, what we do for notation here is we found the antiderivative, but we're not done the question. So typically, notation-wise, they'll put a square bracket here, reminding us that we're not done, reminding us that we're still have to find the integral from -1 to 2. So now what we're going to do is we are going to use our fundamental theorem of calculus. This is our antiderivative. What we have to do is we have to put 2 in for x, minus, we have to put -1 in for x. And if we do that, we will get the answer of 15/4. All right, this is 16/4 minus 1/4. We get 15/4. And fractions are good, and we want to leave our answer in fractions. All right, so that's a fairly straightforward example. Let's do one more straightforward example, and then I'll do a bit more of a difficult one. Let's go back to the other board. All right, here's our second example. I'm going to do this one with you together at the same time. And so what happens is here now we have evaluate the integral from 2 to 5 of the function x squared plus 2 dx. Again, remember this dx is just notation telling us which integral or which variable we're integrating with respect to. The first thing we're going to do is we're going to find the antiderivative. The antiderivative says increase that exponent by 1 and divide by that number. And the 2 has an x to the 0, so we're going to increase it by 1 and divide by 1, which we're not going to write. We're going to use this square parentheses to remind us we're not done. We still need to evaluate from 2 to 5. All right, we're going to put the 5 in first, subtract, then put the 2 in. So here we go. We're going to go 5 cubed over 3 plus 2 times 5. So that's f of b from our fundamental theorem of calculus, minus, now we're going to put 2 in, so 2 cubed over 3 minus 2 times 2. And if you evaluate that and you punch it into your calculator properly, again, fractions are our friends, we will get an answer of 135 over 3, which equals to 45. And it's really just that simple. Now, where this gets difficult in the coming days is these initial functions can get more difficult. Right now, all we're doing is reversing the power rule, right? Power rule, so we take the exponent out front and we decrease the exponent by 1. We're reversing that. Obviously, these functions can get more complicated where we're trying to reverse the chain rule or reverse the product rule or quotient rule. And so again, there are some techniques for integration that we'll look at that will reverse those things, and that's where things can get a little more complicated, but we'll do that in a couple of days. Let's do one more example on the other board, and then I'll tell you what you're going to do for your assignment. All right, here's our last example for today. We are going to look at evaluating the integral from pi to 2 pi of sine x dx. So this is a trig one. Now, if you've forgotten your derivatives of trig functions, you can refer to your formula sheet. So again, this is your formula sheet that you have. It is on Connect. Remember that on one side we have derivatives. On the other side we have all the integrals. And so you can see there that there are a bunch of integrals that you have. And so you can look there. And if you look there, the first thing you'll see is a whole bunch of normal ones. But as you get down to number 6, it says the integral of sine u du. And the integral for that is negative cos. So the antiderivative for this becomes negative cos x. And we're going from pi to 2 pi. All right, so using the fundamental theorem of calculus, we're going to go negative cosine of 2 pi minus the negative cosine of pi. And when we do that, we remember that the cosine of 2 pi is 1. Remember, the cosine is the x-coordinate at 2 pi on our unit circle, and so the cosine of 2 pi is 1. So this becomes negative 1 minus, now here the cosine of pi is negative 1, and we have the negative of negative 1, so that becomes 1, and we're left with 1 minus 1, which equals, negative 1 minus 1, which equals to negative 2 as our answer. Okay, so again, when you're doing definite integrals, this is our notation for doing it. We find the antiderivative first, and then we put in the upper limit, we put in the lower limit, and we subtract the 2, and that gives us the area under the curve, or between the curve and the x-axis, between the 2 points. On Connect, you'll find an assignment. It'll be a handout out of a book, and work on it. This will be the last lesson for this week, so if you haven't finished your test yet, finish your test, do these questions. Next week, I'll spend some time going over them, so ask any questions that you have that you can't get. And then we're going to move into using some of the other techniques of integration in order to solve some more complicated questions. So you can look forward to that. Have a great day, and we'll see you soon.